And then all the Karens can't be like, oh, pull your mask up.
All the Karens.
All right. Let's take a look at today's lesson. This is the last lesson in Chapter 3. We will review tomorrow and have a test Wednesday. So today's just looking at transformations of polynomial functions. It shouldn't be too difficult for us. It's we've kind of looked at some of this in Chapter 2, I do believe. But we were dealing with parabolas then, and now we're just dealing with other polynomial functions. A says, is the graph of f or g symmetric about the y-axis? So basically what that means is, does either graph f or g, does it reflect over the y-axis? Does it look the same on both sides? This one does, right? If this is our y-axis, you see how this looks the same on both sides? So I said f is symmetric about the y-axis. What I mean is it reflects across the y-axis. All right, is the graph of f or g symmetric about the origin? What that means is the graph of f or g identical when it is rotated 180 degrees about the origin? So I'm going to get a pencil and draw this. So if it was rotated, if this graph was rotated 90 degrees, it would look like this right here, okay? And then if the graph was rotated 180 degrees, it would be on top of this line. So yes, G is symmetrical about the origin. So I wrote identical when rotated 180 degrees about the origin. Part B says, graph more functions in the form of y is equal to x raised to the n power, where n is a natural number. Which of these functions are symmetric about the origin and which are symmetric about the y-axis? So, we'll graph this together. So if we had y is equal to x raised to the n power, where it says n has to be a natural number, so that means it's going to be like 1, 2, 3, 4, things like that. So we've already looked at x raised to the third. That was f. We looked at x raised to the fourth. Or no, we hadn't. We've looked at x raised to the second. Right there. All right, so x raised to the fourth. All right, it looks just like the x squared, right? So it's symmetrical about the y-axis. X raised to the fifth is symmetric about the origin. It looks very similar to x raised to the third. X raised to the sixth. It reflects across that y-axis. X raised to the seventh is symmetrical about the origin. So basically what we can gather from this is functions that have an even degree are symmetrical about the y-axis. All right, functions that have an even degree are symmetric about the y-axis. And functions that have an odd degree are symmetric about the origin. So that brings us to our next step, our next problem. Try and get our textbook pulled up for us real quick. Alright, so this says a polynomial function is even, or is an even function if it is symmetric about the y-axis, and an odd function if it is symmetric about the origin. Other types of functions can also be classified as odd or even. For example, y is equal to the absolute value of x is an even function. You notice how we've got even, odd, and neither. Even, remember, reflect that y-axis, it reflects across that y-axis. Odd function is symmetrical about the origin, and then, for instance, this one would be neither. So, example 1. Alright, they just kind of give you some graphs that they want you to identify. They said it's not reflected across the y-axis on A, so it's not even. If you rotate the graph 180 degrees about the origin, is it the same graph? Yes, it is in this case, so it is odd. It reflects across the y-axis right here, so it is even. And then right here, it doesn't reflect across the y-axis, and it's not symmetrical about the origin either, so that means it would be neither. So in your book, you're given these two examples right here, these two graphs. And they want us to determine whether they are even, odd, or neither. So based on what we looked at just a second ago, and what we looked at on those graphs there, is it even, odd, or neither? It is odd, that's correct. Because it is symmetrical about this origin. So what that means is if we rotated it 180 degrees, would it look the same? Yes, it would. Because if you rotated it 90 degrees, it would look something like this. If you rotated it 180 degrees is when it would be right back on the same graph, okay? B, could it be either even, odd, or neither? But it is even because it reflects across that y-axis. All right, now they want us to determine whether the graphs are even, odd, or neither by looking at our equation. So I'm going to do these two examples with us, or with you, and that way we can look at to see whether or not they are even, odd, or neither. So if I've got f of x is equal to 4x to the fourth plus 5. Alright, our first step says replace x with a negative x. So we're going to do that. So I'm going to find f of negative x. So anywhere I've got an x, I'm going to put a negative x. Alright, and if anything is raised to an even power and it's negative like this, if you got a negative times a negative, that's a positive, times a negative, so that would be 3, that would be a negative number. But if you multiply it 4 times, it's going to be a positive number, right? So I've got this equation, 4x plus 5, or 4x to the fourth plus 5. So I want you to write these little notes down here. If it's opposite, if it's completely opposite, so if it would have been negative 4x to the fourth minus 5, it would be odd. It would be an odd function. If it is the same, if it's the exact same equation, it's going to be an even function. And if it is neither the opposite nor the same, that means the function is neither. So do you see how we started with the equation 4x to the fourth plus 5, and we also ended with that equation? So since it is the same, it is an even function, okay? Alright, so now we're going to do those same steps, but we're going to plug negative x in anywhere I've got an x. You've got a negative raised to an odd power. That'd be like negative times negative times negative. That's going to be negative. So this becomes a negative 2x to the third power. 3 times negative x is a negative 3x. So this is what we started with. This is the equation we ended with. Are they complete opposites? See, I started with positive 2, and now I've got negative 2. Positive 3, now I've got negative 3x, right? So since they are opposite, that means that this is an odd function. All right, we're going to do that with A and B here. All right, I told you anytime that there is an odd power with this negative x, that's going to make it negative. So I've got negative 7x to the fifth negative 2 times negative x squared. So anytime negative x squared is a positive x squared times negative 2 to give me a negative 2x squared plus 4. So truthfully, in this one, do you see how this negative 7 was the only one that had a change? So it's not opposite, and it's not the same, so that means it is neither. All right, B, negative x to the 6th minus 2. It's to an even power, that means it's going to be positive. So what's this one, even, odd, or neither? Even. Even, because you see how the equations are the exact same. That's what makes it even. Alright, so this is just looking at the graphs of, or transformations of cubic and quartic parent functions. And so basically what we're going to be doing is the same thing we were doing in chapter 2, where we look at AH and K. So if I go back here to Desmos and I type in y is equal to x raised to the 3rd, that's my parent function. And they want us to see how does this graph differ, or how do these two graphs differ. So I got 2x raised to the 3rd minus 5. So my turning point, or is it 0, 0 for the green graph, and is it 0, negative 5 for the purple graph? And they want us to tell how they are different. Well, first of all, what I do on a problem like this is I figure out what A equals, what H equals, and what K equals. It's just the same as when we were dealing with quadratics. What is our A value from this equation right here? 2. Remember, your H value comes from what's inside your parentheses. And H always lies, K tells the truth. That's still the same. Do I have any parentheses here? No. So what does H equal? 0. And what's my K value? Negative 5. Now we got to remember what AH and K do. Remember, A can either stretch or compress or reflect. H moves it left and right. K moves it up and down. It is greater than 1. That means that it is a stretch. So I wrote stretches by 2. It does not move left or right any because H equals 0, but it says K is equal to negative 5. So what does K tell me it does? Moves which direction? Let's actually look at the graph. Which direction did it move? Move how much? The green was our original. The purple is our transformation. So it moved down, right? And it moved down how many units? 5. So it moves down 5. Everybody got this? All right, next page. It says determine the equation of each graph as it relates to its cubic function or quartic function. So this one, cubic, cubic parent function is y is equal to x cubed. Quartic parent function is y is equal to x to the fourth. So first let's kind of identify what type of function this is. Is it a cubic or a quartic? Cubic would be y is equal to x to the third power, and quartic would be y is equal to x to the fourth power. So let's look. This is x to the third power. Does it look kind of similar to x to the third power? Is A? Yeah. And this is y is equal to x raised to the fourth power. Does that one look similar to B? So I'm going to say A is cubic and B is quartic. So this turning point right here is going to be very important information for us. This turning point is at 2, 1, 2, 3, 4. So if you remember back from quadratics, your vertex gave you h and k, right? Well, this kind of acts like a vertex. This is what we call a turning point. So I'm going to say A equals, H equals, K equals. Well, H equals 2 and K equals 4. But there is one thing I noticed. Do you see how this graph starts up and ends down? But this graph right here starts down and ends up, doesn't it? How do you think I might can make it do the opposite? How do you think I can make it flip? Make it negative. Let's see if that works. Did that work? Mm-hmm. Yes. So, we know that A has to be negative. So I've got y is equal to A times x. Remember, h lies. So if this says h is 2, what is h really? What are we going to write? We're going to write minus 2, right? We said it was cubic, so instead of writing to the second power, what power am I going to write it to? The third plus 4. All right, our vertex here is at negative 1. Negative 3. Because it opens up, that means that A is still positive, so A is an understood 1. H is negative 1, and K is negative 3. So my equation would be y is equal to, if A equals 1, we don't have to write it. X plus 1, because remember H lies. We said it was quartic. So x plus 1 to the fourth power minus 3. All right, our last example. The volume of a cube in cubic feet is given by the function b of x is equal to x cubed. Write a function for the volume of a cube in cubic inches. So how do we go from inches, how do we go from inches to feet if x is the edge length in feet? So how many inches are in 1 foot? 12. So in order for us to write it in inches, we have to take x cubed and replace it with 12x cubed. Why did we use 12? Because there are 12 inches in 1 foot. So I go to my calculator here. 12 raised to the third power is 1,000. 728, and then we've got x cubed. So this right here would be my equation for the volume of a cube in inches. Instead of feet. A storage unit in the shape of a rectangular prism. The volume of the storage unit is given by f of x is equal to x times x minus 1, where they say that x cubed minus x squared is our equation. It says where x is measured in feet. A potential customer wants to compare this volume of this storage unit with that of another storage unit that is 1 foot longer in every dimension. Write this function for the volume of this larger unit. So this is my equation of my original unit. So if I want to figure out what my equation of this new storage unit would be, it says it is 1 foot longer in every dimension. So I'm going to say x plus 1 cubed minus x plus 1 squared. So do you see everywhere I had an x, I replaced it with x plus 1 because this storage unit is 1 foot longer in every dimension. So if I've got x plus 1 times x plus 1 times x plus 1, if you want to use box method, you can, or you can just use regular distributive property. So I'm just combining my first two together right now. So I've got x times x, which is x squared. X times 1 is 1x. X times 1 is 1x. And 1 times 1 is 1. So I've got x squared plus 2x plus 1 times x plus 1. And I'm going to use that box method again just because I think it's a little bit easier. I have a graphic organizer for us. This is x cubed, 2x squared, 1x. X squared, 2x, and 1. X cubed plus 3x squared plus 3x plus 1. Alright, so now I'm going to replace x cubed and x plus 1 squared. So I've got x cubed plus 3x squared plus 3x plus 1. That's x plus 1 cubed. Minus x plus 1 squared. We did that right here, correct? X squared plus 2x plus 1. The first thing I did was x plus 1 times x plus 1, right? So that's the x plus 1 squared. Now I've got to distribute this negative. X cubed plus 3x squared plus 3x plus 1 minus x squared minus 2x minus 1. Combine any like terms. I have nothing to combine with x cubed. 3x squared minus x squared leaves me with a positive 2x squared. 3x minus 2x is a positive x. And then 1 minus 1, they just cancel each other out, right? So my new equation for a storage unit that would be 1 foot longer in each dimension is x cubed plus 2x squared plus x. Alright, you can get started on your homework if you want. It's in Schoology. Remember, it is due by tonight at 11:59. So we'll do homework or you'll do homework tonight, turn it in, and then we'll do your review tomorrow and test on Wednesday.